It's December 19, and we're gonna talk about an interesting article in 2008, which has got around 57 citations, and it is called embedding of negative type metrics and an improved approximation to generalized sparsest cut. And it is written by people like Shushi Chawla, Anupam Gupta, and Harold Reiki. So far we have talked about generalized sparsest cut, but now we're going to see how it could be useful, how a new algorithm based on measured descent could be useful for generalized sparsest cut. So when I say negative type metric, we mean that, for example, first we have vertices V and we have a metric D. But if root of D is an Euclidean metric, it means that, L2 squared matrix. So you can say that, so for a negative type metric, you can say that your space X and your root of D embeds isometrically into L2. So we go from space X into L2 isometrically, and as you know, the distance between X and Y, so because it is isometric embedding, so this becomes equal to this squared. And about SDP relaxation of sparsest cut, so you know that integrality gap is equal to worst distortion required to embed endpoint metric of negative type into L1. So what is the goal? The goal is you have a negative type metric, you have endpoint negative type metric, you embed it into L2 with some distortion. Distortion is log 3/4. And this implies, so after you embed your negative metric into L2, this implies that you already have order of log 3/4 K approximation for sparsest cut with non-uniform demands. You mean K sinks and K source. So K in this means you have K source and K sinks. So first you embed negative metric into an L2 space, and then this implies that you already have a good approximation. This is a relatively good approximation for sparsest cut. And as you know, and James has talked about these things in Simon's Institute several times, that L2 metric is just a subset of L1. And L1 is itself a subset of negative metrics. So it's negative metrics, so it's quite a good generalization, tight generalization of L1 metrics. And if you are in L1, you can isometrically embed it into L2. So only this is important if you embed it into an L1. So there is a theorem in this article that, for example, says that given a negative type metric and a set of terminal pairs, you have a set of terminal pairs, and you know that your terminals, the cardinality of terminal set is K, and so there is a contracting embedding. So you go from V to L2 such that for all pairs X and Y in your terminal set, this is a contracting embedding. It means that f of x minus f of y should be greater than, so we can get this log 3/4 k d of x and y. So this contracts your original space, distance in your original space, and then the distance is in the embedded space is contracted. So if you have if you give a negative type metric to an algorithm, and you give a set of terminal pairs, then there is this contracting embedding phi, such that this relationship holds. Also, there exists another theorem that there exists a randomized polytime algorithm, log 3/4 k approximation algorithm for sparsest cut with non-uniform demands. And the proof is very simple. The proof, it says that distortion D and distortion embedding into L1, so it becomes the integrality gap for SDP of sparsest cut. So if you just check the integrality gap for SDP of sparsest cut, you see that it's just D. It's just your distortion. And it's very interesting that relates the sparsest cut problem, and we can take advantage and use the metric embedding paradigm for something like something important like sparsest cut problem. And so in this paper, we classify terminal pairs in D by distance scales. For example, we say that all of the pairs X and Y, terminal pairs, that have distance around 2 to the I, they should go to the same strip, let's say, to the same space, same set. So DI is just all X and Y such that their distance is in this bounded space. So we say that it's like, so here we go and 2 to the I plus 1, and everything here, every two pairs, their distances is less than this. So this could be one thing, this could be one thing. So at most your distance is this. So the distance between X and Y is their distance is limited. It's something between 2 to the I and 2 to the I plus 1. So for example, if you have a reference point here 0, then their distance here is 2 to the I, and here is 2 to the I plus 1. So we are trying to partition the vertices, all of your vertices, and terminal pairs into some spaces Di, such that, for example, this is D1, this is D2. So you have many different scales. Why this is important for me? Because in stochastic block model, you have some space, and it's some you have some ergodic space, and you want to select, you want to understand the structure of this space. So you try to find all of these pairs, and their distance is between 2 to the I and 2 to the I plus 1. For example, you don't collect these spaces because from information theoretic point of view, these 2 points don't give us any information. Our structure is something like this. It should capture this structure. Anyway, I just want to say that when we say good events, we mean X and Y lie in different component of partition. For example, in DI, you have a set of DI. If X and I lie in different components, for example, X in D1 and Y is in D2, then they are connected and they belong to different sets. So it's a good event. And another good event is that the distance from X to any other component is at least eta 2 to the I, where eta is 1 over order of root log k. And the same for Y, of course. And it's like maximum cut on terminals. You want to encourage those terminals to go from one cluster to the other cluster only if they are terminals. It's like, let's say, Steiner tree. You want to connect those terminals together and not other points. Other points are not interesting for us. And so you can look at so to get an embedding, we want a partitioning that separates a random constant fraction of pairs in DI. So remember that phi is minimum of all of the cost between U and V, D and U. This is the generalized sparsest cut because now we have demands and capacities, and DI, D of SI and TI. So if the distance between your terminals goes up, your phi goes down. And a multi-commodity flow, we can see it as a graph embeddings. So every multi-commodity flow can be viewed as an embedding of G prime, V, E prime, and Dij, and these are demands, on the same vertex set, such that the weights of the edge I and J is Di and J. For example, let's say it is I, this is J, and they are connected, but a cut comes. So this is a cut, and this is a part of this graph. G prime is V and E prime and Dij. And you know that alpha of G prime is less than alpha of G. I've shown this in my other lectures. So you have some, for example, let's say this cut here, and this corresponds for the graph G equal to V and E. And from all edges, we just have a selection of E prime. And we want so the edge expansion, alpha of G, the edge expansion is minimum of all edges that goes cross. And this is the approximation of sparsest cut. because you are trying to approximate it by some terminals. You're trying, I don't say Steiner tree because it's a different topic, and of course it's a generalization of everything. Steiner tree is very important problem, and it has interesting connections to tree packing, anything you could imagine, vertex cover, and anything that is interesting. So the generalized sparsest cut, you have k-sink and source, Si and Ti. So when we say D of S and S bar, it means the net demand going from terminals in S to those outside S. And when we say C of S and S bar, it means the total capacity of edges exiting S. So now we can define your phi, which is minimum of C of S and S bar, over the demands for any S that is a subset of your vertex set. And this is equal to minimum over all cut matrix delta S of CUV delta UV sigma DI delta S SI and TI. And this is a minimum of, now D is in L1, so it's a L1 metric, and CUV DUV DIJ, distance between SI and TI. So unit demands relates to traditional. When we have a unit demand, so it's like traditional sparsest cut problem. But when we optimize over all metrics, and then we round the solution. And this is NP hard problem. And what we want to do is that we first optimize over all negative metrics. We optimize it, and then we round it. So in general, you can think of metrics as just some points. This is something that James has explained in his lectures, and this is the L1 metric. And because negative metrics is a little harder, so we try to approximate a negative, this is negative metric cone, all inside. So we try to approximate it by L1 metric. Why is it important? I said before, because if you have a phi of negative metrics, what is this? What is your sparsest cut? What is this dp relaxation of this problem? It is the sum over CUV DUV over, the minimum is over all negative type metrics. And demands here. And now what is interesting is that if we could somehow prove that this distance, so this D is a negative, remember D is a negative metric. If we could somehow prove that this is greater than some constant factor of your L1 metric of U and V, as you know, this is just U minus V L1 metric. Because L1 metric is inside your negative metric, so it's a relaxation. What I want to say is that phi of negative type, phi of neg, is just a relaxation. So if you find it's always less than your phi. So if we embed negative into L, negative metrics into L1 with some distortion at most D, then we can say that our phi is less than D times phi of negative. And it's very interesting because now remember that phi of negative type is always greater than phi. And this is